Right, so did we complete this process? Did we see the derivation here? But I remember explaining you what is self-induction. Do you remember that? So for self-induction, can you tell me what is the process? Hmm? To those who are online, am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Raya?
Yes, sir. Yes, sir.
Okay. Okay. Just a minute. Okay. Guys, just a minute. Right. Yeah. So can you tell me what is the process that we discussed for self-induction? Can you explain? What did I say for self-induction? Pranav, you tell me. Is the magnetic field going to induce the EMF? That's not what I told you, right? So magnetic flux will induce EMF. Is it right? That's not what I told you. You tell me. What did I say for self-induction? What kind of a process is that? You didn't use the word change in flux. You told flux will get generated, which will generate EMF. That statement is wrong. You should mention that there is a change in flux that is going to induce EMF. Yeah, you tell me, complete it. Is it only during the process where the current goes from 0 to some steady state value? From steady state to 0 is also possible. That is the second case, right? When both of them happens, there will be an EMF induced. So you tell me, what is the name of that EMF? There were three names that were given. I told you. One was called, what is one name? Back EMF is one of the names. Next. Also called induced EMF. It is also called opposing EMF. Right? Why do we call it as opposing? Because it will try to oppose the process. Right? Now, you have a coil like this, right? And let's say it is connected to a battery and the switch is closed. Right? Tell me, what is the direction of current due to the battery? Clockwise. Now, Sydney, you tell me, in which direction will the induced current flow? The same direction? Divya, you tell me. Same direction. You mean to say induced current is in this direction? Same direction? Same direction. It is why? I gave you the reason for this also. Did I give you a statement? Something like a proportionality relation? If one increases, that's the reason. So the induced current will be in such a way that it will be in the anti-clockwise direction when the current is trying to grow. So this kind of current, which is increasing with time, is called as growth of current. Which current is growing? The current supplied by the battery is growing. Whereas when you open the switch, what is happening? There is a decrease in the value of current. This kind of a current is what is called as decay. In the sense, it will try to decrease. See, this word is not much used in your textbook, but you can just make a note of it to understand. What do I mean by growth and decay? So growth of which current? Make a clear note of it. Growth of which current? Growth of the current supplied by the battery. Okay. And decay is the decay of the current supplied by the battery. Right? Now, the next point that we are supposed to see is self-inductance of a long solenoid, right? Self-inductance of a long solenoid, okay? Yes. So topic is self-inductance of a long solenoid. Here, the meaning of long solenoid is thickness of solenoid is very much greater than, sorry, am I not able to see? Okay, listen. So here, when I say self-inductance of solenoid, right, of a long, here the meaning of long is of solenoid is very much less than the length of the solenoid. That is when it can become a long solenoid. That is the meaning of long in this case. Okay. So our job is to derive the self-inductance of this. But if you recollect, we saw that the flux generated across the coil is directly proportional to the amount of current that was flowing through it. Right. So when you remove the proportionality symbol, the constant that you've introduced is L. So it is L into I. So L will be equal to N into phi divided by I. So what we need to find in this case is what is the value of L for a long solenoid. That is the meaning of this statement. Okay. So if I take a solenoid which is long enough, right? So let us consider a long solenoid of length L, and radius very much less than that of L. So its radius is going to be very small compared to the length of the solenoid. So when the radius is small, its area will be small. When area is small, you can say that the thickness is small. So thickness is going to be very much less than the length of the solenoid. Okay. And it is having n turns per unit length. Remember, the number of turns is always represented by the symbol capital N, and the number of turns per unit length is represented by the symbol small n. Okay, that is how the notation is. So if a current I flows through the coil, then the magnetic field inside the coil is almost constant and is given by the expression B is equal to mu naught into N into I, where mu naught is going to be the permeability of free space, small n is going to be the number of turns per unit length, and I is the value of the current that is flowing through the coil itself, and this value is to be remembered. So this is going to be the value of magnetic field inside a long solenoid, right? So we are going to start our derivation with this expression. First question to be answered is, since we are expected to calculate the self-inductance of a solenoid, I know that the formula for self-inductance capital L is equal to how much? N into phi divided by I, right? So this solenoid is going to have n number of turns multiplied with what is going to be the flux that is associated with the solenoid. So we know from the concept of self-induction that the current flowing through the coil is the reason for its induced current. So the current flowing through the coil itself is generating the induced EMF, or it is inducing the EMF unit. Am I right? So here, if you observe, what is the amount of current that is flowing through the coil? It is this I. So how much is the value of flux that is associated due to this magnetic field? It is given as B multiplied with A, right? It is B into A into cos theta, the whole divided by this I. Am I clear with this expression? So what I did is, in the place of I wrote the formula for it, but the only question I need to answer is, who is producing the magnetic field? So in this case, the magnetic field is produced due to the own coil itself. That's why it is self-inductance, right? So L is equal to capital N, I'm leaving it as it is. So I know the formula for B, which is given as mu naught into N into I, and area I'm leaving it as it is. Into, the question is, what is cos of, how much is the angle I need to write here? Listen to this carefully. Due to a solenoid, the magnetic field inside, I'm talking about a long solenoid. Due to a long solenoid, the magnetic field inside will be parallel to the axis. It will be parallel to the axis. And remember, the coil is in this way. When the coil is in this way, the aerial vector is also parallel to the axis. So let's come again. What did I say? Magnetic field is going to be parallel to the axis, and the aerial vector is also parallel to the axis. So what is going to be the angle between B and A? It is going to be 0 degrees. So I need to write cos 0 here, the whole divided by, it's going to be I. So this I and I will get cancelled. So this clearly indicates that the self-inductance of a solenoid is independent of the amount of current that is flowing through it. Right? I is not there anymore. So when I write the expression here, right, when I write the expression here, it will be N into, what can I write in the place of other values? So it is going to be mu naught into N into, there is no I anymore. So mu naught into N into A into cos 0 is going to be 1. That is all we are left out with. So there are two things that we can do here, right? One is, if you observe, we can write small n is equal to capital N divided by L. So when I do that, in the place of small n, I can write capital N divided by L. If I write it, then I'll get this as N into mu naught into capital N divided by L into A. And when I multiply both, it is going to be mu naught N square A, the whole divided by L. Right. So this is going to be the expression for self-inductance of a long solenoid. But this is one such expression. Okay. So it is mu naught into capital N square A divided by L. But what is the other thing you can do? You can write capital N is equal to small n into L. Right? Capital N is equal to small n into L. In the sense, in the place of capital N, I can replace it with small n into L. If I do that, what am I going to get? So I have N into mu naught into small n into A. What did I say now? Capital N is equal to small n into L. Take it and plug it here. Then what are you going to get? You will get mu naught into N into A. And outside what you have, it is N into L. Right. So this will be equal to mu naught N square A into L. So this is another expression. And the third expression that we can write is, I leave it as it is. So I leave mu naught N square A into L as it is. I'm not disturbing N, but I'm going to change the value of A as pi r square, because the cross section is going to be a circle, right? So it is going to be mu naught into N square into pi r square into L. So it will be mu naught N L into pi r square. So this is a third expression that I can write. So if you observe, the self-inductance of a solenoid itself can be represented in three ways. What are they? Mu naught capital N square A divided by L, or mu naught small n square A into L, or it is mu naught N, it is actually, yeah, mu naught N square L into pi r square. So let me write all the expressions here. So capital L will be equal to mu naught into capital N square A divided by L. This is the same as mu naught small n square A into L is the same as mu naught N square L into pi r square. Right? So these are all the expressions. So depending on what is the data given in the problem, you can use the right expression to solve it. Is that clear? So if suppose in a problem, they are concentrating on the number of turns and length separately, then you can use this. So if they're concentrating on number of turns per unit length and length separately, you can use this. If they're concentrating on number of turns, length and radius, you can use this. Is the point clear? Okay. So make a note of this. Shall I proceed? Yeah. Listen. So listen. The next topic we'll discuss is mutual induction, right? So as the name suggests here, mutual means, unlike the previous case, it was called as self-induction. So self means it is with its own, whereas mutual means here it is going to be one with respect to another. Am I right? So in this case, what you will have is you will have two coils. Listen to this carefully. You will have two coils where one of the coils will be connected to the battery and the other coil will be connected to a load. So when I say load, it can be any electrical load like a galvanometer or a small LED bulb or a resistor, whatever it is, where you can detect the presence of current. Okay. So here, if you observe, we have one coil which is connected to the battery, and there is another coil which is connected to a galvanometer. If you observe, this is a thing. So you have one coil here which is connected to the switch. So coil connected to the switch and the battery is here. So this coil is the one which is connected to the battery. And the other coil is this one, which is connected to the load. Here it is a LED. So what should happen in this case is, the logic is very simple. Like the previous case, when you are going to close the switch, right? I'll tell you the name of these coils later, but listen to the logic clearly. When you're going to close the switch, what will happen? So there is going to be a current that will grow from 0 to some value, 0 to a steady state value. See, that current is generally called as transient current. It is not mentioned anywhere, but you can just know the name. It's called transient current. TRANSIENT. It's called transient current. And what that current will do is, due to the increase in its value till it reaches a steady state, right? So since it takes time to reach the steady state, in this process, there is going to be an increase in the magnetic field. So what is going to happen? I will increase, due to increase in I, B will increase, and due to increase in B, there is going to be increase in flux. So, but we know due to a solenoid, due to a coil, what will happen is the magnetic field is going to be like this, right? So if these two coils are placed close to each other in such a way that the magnetic field produced by the first coil is able to cut some flux through the second coil. So what is happening? See, the one I drew is not actually entering the second coil, but there will be another magnetic field line which will enter like this. So what is happening? Initially, the current through this is 0, so magnetic field was 0. So is the case with second coil also. But what happened, as the current grew in this, the magnetic field also grew, due to which flux grew. So the flux generated by the first coil is getting linked with the second coil, due to which there is a change in magnetic flux taking place in the second coil, and an EMF is induced, which can be detected with the help of a galvanometer. So this kind of a process where the change in flux in one coil is able to create an EMF in the other coil is what is called as mutual induction. Is the point clear? So as I told you here, this coil connected to the battery, when I switch it on, right? There's just a push button. When I switch it on, what will happen is there will be an increase in the value of current in this. So during that process, there will be some flux associated with the second coil, and there will be an EMF induced, due to which this LED will start glowing. But it will glow only till the time there is a change in flux. So if you observe, it will glow only during the time I press it, means the current is growing, and when I release it, when the current is decaying. You're able to understand? So pressing, you saw that the LED glue, it was just blinking. Now I'll release it, see what will happen. Did it blink? No. Actually, it should happen. Okay. So when you release it also, the same thing is going to happen. Right. 1 minute. Yeah. So listen. So I hope you understood what is mutual induction. Right. Now my question is, there is going to be a flux associated with one coil, which should be directly proportional to the current produced by one coil. Right. But before that, you should know what are the names of these coils. So the coil which is connected to the battery is what is called as primary coil. The coil which is connected to a battery is called as the primary coil, and the coil which is connected to the source, the coil which is connected to the load is what is called as the secondary coil. Are you able to understand this? Right. So when I write N into phi is directly proportional to I, tell me one thing logically. In this case, current can flow through which device? Current is supplied by which device? Is it due to the primary coil or the secondary coil? Primary coil. So if I take this coil as 1 and this coil as 2, can I just use the subscript like the flux associated with the second coil, that is N2 phi 2, is directly proportional to I1? Makes sense? Right. So N2 phi 2, if I remove the proportionality symbol, I need to introduce a constant, and that constant I'm introducing is capital M. So in the previous case, it was capital L that was introduced. Right here, it is going to be capital M into I1. But the only difference is, there we did not use any subscript. Here we'll be using a subscript like 2,1. So this capital M is what is called as mutual inductance, but it is going to be a relative term. Like you will either write it as M21 or M12. So it is mutual inductance of second coil with respect to the first coil. You're able to understand? So M21 will be equal to N2 phi 2 the whole divided by I1. Make sense? So is it not looking similar to the expression we saw for self-inductance? Right? It's the same thing, but the only difference is you need to be exact with your subscript that you're going to use. So if it is going to be M21, remember it is very easy. The first number should be in the numerator, second number should be in the denominator. That's the idea. Suppose I interchange and write it. See, suppose I take this as the first coil, this as second coil, because numbering is in my hand. Suppose I take that as first coil, this as second coil, then what will happen? Then I can write N1 phi 1. See, this is only an alternate information. Right? It is not correct with respect to this diagram. It is only an alternate information. It is not correct with respect to this diagram. For this diagram, there is a logic. Okay. But the other thing is, if I write N1 phi 1, you tell me what am I supposed to write on the other side? So flux induced by one coil is possible only when the current is changing in the other coil. So if I write 1 here, I should write 2 here. So N1 phi 1 should be equal to what? M12 times I2. Right? Then what is M12? It is N1 phi 1 the whole divided by I2. So this is how it works. See, you're able to understand? 1 in the numerator, 2 in the denominator. That's how it works. Okay. Now, from this expression, if I observe, right, I know that N2 phi 2 is equal to M21 times I1. See, first of all, this is one of the definitions of mutual inductance. The next thing is I need to know what is the relation between EMF and mutual inductance. So for that, if I differentiate on both the sides, what will I get? So T of dt of M21 times I1. Right. So that implies what is d by dt of N252? It is the negative of EMF. Right. So this is basically the EMF that is induced in the second coil. Right. It is the EMF induced in the second coil. This will be equal to M21, I can take it out into, I will write dI1 divided by dt, which implies M21 is equal to minus E2 divided by dI1 divided by dt. Is the point clear? Right. So M21 will be equal to minus E2 divided by dI1 divided by dt. This is another expression for the same mutual inductance in terms of EMF and the rate of change of current. Right. So we also know another point. So how is flux measured in? It's measured in terms of Weber, and how is current measured in? It is measured in terms of ampere. This Weber per ampere is what is called as Henry, and it is represented by the symbol capital H. Am I clear with this? Right. So this is all about the introduction of what is mutual induction. So make a note of it. What happened? Does it have any rate of change of current order? Did I tell you what is the significance of an inductor? You try to oppose the, it will not allow the current to change within it. That's why the di by dt. Shall I proceed? So, yeah. So like the previous case, right? Like the previous case, we need to derive the mutual inductance, but this time it is not going to be mutual inductance of one solenoid, it is going to be of two solenoid. So mutual inductance of two long solenoids. So if you observe this, right, in this case, what is going to happen is there will be one solenoid, right, which is the primary one. The pink is one, which is called as the primary. Okay. So there will be one solenoid and another solenoid placed exactly along the axis of the first solenoid. So you're able to understand this? So there is another solenoid, right, which is represented by the dotted circles. That is another solenoid which is placed coaxial with respect to the first solenoid. In this case, what we have done is we have taken both the solenoids to be of the same length, L. But here, what are the parameters that will change is the number of turns associated with each coil and the radius. So the radius of each coil is going to be different. One will be R1 and the other is going to be R2. Here, if you observe by diagram itself, you can understand that R2 is greater than R1, right? So if you observe this case, right, you can ask me, why are the solenoids connected in this way? The reason is very simple, okay? If you take one coil like this, another coil like this, right? If you're going to place them in this way, let's assume this is one coil, this is another coil. If you're going to place them in this way, where one is connected to the battery, then this will be called as the primary. And this one is connected to the load, which this will be called as the secondary. So there is going to be a magnetic field generated from this, which will come out and it should get linked here, right? When it should get linked, if you place them close, maybe there is good level of linking that is taking place. But if there is a slight displacement like this also, what will happen compared to the first scenario, there might be a decrease in the value of the flux getting linked between the first and the second coil. Whereas if you place them like this, right, if you place them coaxial with respect to each other, then what will happen is whatever flux is generated by one coil will completely get linked with the second coil. So if you observe, right, the best way of connecting, right, the coils to produce a maximum mutual induction, right? To observe the maximum mutual induction is placing them coaxial with respect to each other, right? So that is the reason why we have considered this scenario and we are going to derive the mutual inductance in this case. So as I told you, right, what I'll do is I'll derive two values. I'll derive M12 and M21. Okay, so listen. So in this case, first I'll start with M21. So what is M21? M21 is equal to N252 the whole divided by I1, right? So this is something important. Listen to this carefully. What did I say are different? The number of turns the first coil and second coil are taken to be N1 and N2 respectively. Similarly, the radius of the first coil is taken to be R1 and the second is taken to be R2. But the length of the first coil and the second coil are going to be the same, which is taken as small l. Okay. And we are deriving the value of M21 in this case. So when I derive M21, observe, it is going to be the number of turns in the second coil. But what is going to be the flux associated with the second coil? Observe. I will write it as dA cos theta, right? The whole divided by this I1, I'm leaving it as it is. So this is where I need to focus on. Everything else is same. So this is where I need to be careful. Now tell me, the magnetic field is produced due to which solenoid? Is it because of the first or the second solenoid in this case? So if you look at the current, you will be able to see. Current is flowing through the first coil. So magnetic field will be generated due to the first coil. Am I clear with this? So magnetic field is generated due to the first coil. But an important point to be noted here is for a solenoid, the magnetic field is going to exist only within the solenoid. So when you talk about a long solenoid, the magnetic field due to a long solenoid is always going to be only present within itself. Outside, the magnetic field is zero. When that is the case, if you observe, the smaller coil is the one which is producing the magnetic field. So where is the magnetic field associated? It is completely there within this pink color coil. Am I right? So how much flux will get linked with the bigger coil? Magnetic field produced by the first coil into, what do we generally write? It should be the area of the, which coil? First coil or second coil? Listen to this. Magnetic field is produced by the first coil, but the flux should get associated with the second coil. So what should I write in the place of A? Should I write it as A1 or A2? So we tend to write A2, but that is wrong. Because since the magnetic flux is associated only in this area, the total flux that the first coil can produce is associated within itself. Am I clear with this? So what I'm trying to say is, see, I'll just give you a logic. Listen, if there is a charge Q and there is a sphere, okay, of radius R, what is the flux produced by it? Flux is equal to Q divided by epsilon naught. Now, if I increase the radius from R to 2R, is the flux going to get doubled? What will happen? The flux is still going to be the same. Why is it so? Because the flux that is going to get produced is because of this charge. In a similar way, I'm just trying to connect the logic here. Listen to this carefully. This is a smaller coil. Pink is a smaller coil, accepted? The black color one is a bigger coil. So though the coil is bigger, what is happening is the total flux is produced in which region? It is produced only within this pink coil. Outside that, there is no magnetic field. Because for a long solenoid, outside it, there is no magnetic field. So what is happening? The total flux is getting locked in this area itself. That is why, though we write it as phi2, but the flux is decided only by the magnetic field produced by the first coil and the area of the first coil. So don't make the mistake of writing it as A2. This is a very, very common mistake. I hope you got the logic of it. Why is it so? Because the total flux is locked within the pink color loop. That is a pink solenoid here in this. Clear with this? So apart from that, everything else is same. N2 into, what should I write in the place of B1? It will be mu naught into N1 into I1. Area, I'll leave it as it is, A1 into cos of how much will be the angle? Same logic. It is going to be cos 0 because magnetic field is along axis, aerial vector is also along axis. It is going to be cos 0, the whole divided by I1. I1 and I1 are lost. They get cancelled. So what will you have? Mu naught into small n1 into n2 into a1. Right. So this will be equal to mu naught into, I know that small n1 can be written as capital N1 by L. So it will be mu naught into n1 into n2 into a1, the whole divided by L. So this is one such expression. In a similar way, how can you write N2 as? Capital N2 can be written as small n2 into L. So, or mu naught into n1 into, I can n2 into L into a1, which implies this will be equal to mu naught into n1 into a1 into L. This is another formula. So remember, whenever you have L in the denominator, the numerators will be capital N's. Whenever you have L in the numerator will always, so there is no denominator for it. When the L value is in the numerator, the N values are small n's. That is the number of terms per unit length. Am I clear with this? And thirdly, how you can write is you can substitute the value of A1 itself, which is pi R1 square. Okay, these are the three values that we can use, right? So there is a one which is given in your textbooks, but you can remember the other also. Am I clear with this? First, make a note of it. You're done with this? Done. So I have to do the last point. I'll do it faster. Listen, we have to do the exact reverse of this. In the sense, we derived M21, right? Now we need to derive the value of M12, right? So if you observe, can I rub this completely? So now we will derive the value of M12. So what does M12 state? Mathematically, it should be N151 divided by I2, right? So what is N1? Leave it as it is, N1 only. So what are the flux associated with the first coil? It is going to be BA cos theta, the whole divided by, here it is going to be I2, right? So this is the only line we need to be careful with. Now the magnetic field is produced due to which coil? The denominator will tell you the answer. If I2, it is a current produced, current flowing through the second coil. So when I say that the current flowing through the second coil is I2, then B2 is going to be in this region. B2 is going to be in this region, right? But the question is, how much is the flux that is associated with the first coil? Though the magnetic field is present outside, we know that the fact that the flux can be associated with the coil only inside it. So how much is the area of the coil which is getting linked with the magnetic field? It is still A1 only. So what I'm trying to say is, whether you're going to write the flux for the second coil or the flux for the first coil, you should always write the area of the smaller loop. That is what both the derivations we did know. In the previous case, the total magnetic field was there inside pink coil, and the area also was associated only for the pink coil. So that is why I wrote the flux of the smaller coil. Whereas in this case, what is happening, though the magnetic field is existing outside the primary coil also, but since I need to calculate the flux through the primary coil, I need to take the area of the primary coil alone. I will only count the number of field lines that are passing through this area. I'm not concerned about the field lines that are out of this area. That is why I took it as A1. See, if this step is clear, everything else is simple, right? So this will be equal to N1 into, what is the value of B2? Mu naught into N2 into I2 into what is going to be the value of A1? Okay, A1, I leave it as it is. So cos of 0, the whole divided by I2. So I2 and I2 will get cancelled. So what are we going to get? You will have mu naught capital N1 into small n2, I can write it as capital N2 by L. So I can write it as capital N2 by L into this A1 is left as it is. So mu naught N1 N2 into capital A1 divided by L is what is going to be the value of M12 also. But if you observe one thing clearly, in terms of magnitude, M12 and M21 are the same, provided you consider two long coaxial solenoids of same length. If you had considered them to be of different length, then you would have got L1 and L2. But if you consider them of the same length, it will be the same value for M12 and M21. Am I clear with this? Raya, do you have any questions?
No, sir.
Okay, we'll wind up. So I'll be completing the chapter by tomorrow. Okay.
Yeah. Thank you, sir.
Yeah.